Hey guys, welcome to a new live stream. Still need to get into things, but we're getting there, Oh, that was a bit too loud. Let's see, is the video and audio good? Should be. Nothing really changed. Good evening from Cape Verde. Wow. That's a long way away. I'm actually not expecting too many people tonight because it's hot summertime over here. It's probably in most of the world or that watches the stream, so 5 by 5. All good. Video's a bit bright. Yeah, we're still in the daytime, and I like setting everything manually on my camera, but it'll adjust over time once the sun settles. Will there be... Oh, I need to lower the music. Something like that, I think. Will there be Ultra? We can make some Ultra. Ultra magic smoke. Maybe. We'll probably try and melt some stuff, actually. But yeah, we're doing a twofold today. We're doing a load test. And during that load test, we'll probably melt some stuff. Yeah, I wanted to see if that new heart feature is now working on the chat too. Could somebody do one of those hearts? Melting some LED strips sounds like Quinder has gone bit loony. Well, somebody's got to fully load test these things, right? Speaking of, I actually need to... I don't think the heart is already working on the chat overlay. That's too bad. No, I don't see it in the chat overlay. Oh well, I see it on my pop-up, but yeah. But speaking of, I need to detach some cables. I forgot to do that. So, I'll be right back. Because I think I need these cables. Yeah, these are 10 gauge. I want them. Because we'll be needing 2 sets of 10 gauge tonight. There. Well, I'll disconnect them all. There. Then at least we don't have to do that during the stream or make new cables. We could, but yeah. There we go. Any streams that start with the expectation of melting shit, I'm in. Nice. Yeah, so I needed these. These are 3 sets of 10 gauge. And since we'll be drawing lots of amps, we'll probably need them. I think there's 3 sizes. No, they're all the same length. Good. Hello, everyone. Hello there, Joe Galaska. I need to clean some stuff off my desk. I shot a Quinbox and now my whole desk is taking over with random crap. There's a lot of tape here. Okay. It's so hot in the Netherlands, it's unbelievable. Yeah, and I'm in my uncooled garage while the house is nice and cool, so... And then I decide to do load testing, which will generate hundreds of watts of heat. Excellent plan. When does the melting and burning begin? I don't know. We'll see. We'll see. I have to, you know. You want to see what I was working on last night? Oh, it's not in the shot anymore. There. Oh no, the antenna came off. It's a AN Mini, which I was playing around with, but not with ESP Home on there, but with WLED. So let's see if it explodes if I turn it on. It shouldn't. Even though, oh, there it goes. Okay, yeah, it went straight to orange. WLED orange. Let's see which IP it got. And I should be able to share that window there. I need to make it smaller there. So this is the AN Mini running WLED, and we are having analog power here, so we can do red, and we can do blue, and we can do green. At the attic with the laser cutter, loving the heat. Oh my god. That's going to be hot, yeah. So yeah, you know, WLED, there are some effects, but for some reason, if you only have one pixel, there's not too much you can do. You can do like the fading. That works. But all the other effects are gone. I don't know why. Oh wait. Like that. So there's no effects here. But if I add a random pixel, let's say I add one pixel, right? One. And, I don't know, give it some kind of GPIO there. Save. The blinking, of course, continues, but now we have all the effects. Now, most of these are kind of useless, but we can do color loop, for instance. I mean, that works, right? It's really bright. I need to lower the brightness. Can you do pink? I can do pink. There, let's see. Pink. Pew. That's pink. We can do ultra brightness pink. Yeah, I'm even in a pink hue now, because this is 54 watts of pink. Oh, speaking of, we might want the power supply camera tonight, don't we? So maybe I should set that up. I should have another lens here, I think. Looks purple to me. Purple. Oh, okay. Hold on. I'll make it more pink. Is this more pink? Like that? Let's give it more brightness. There. So this should be a 42.5mm lens. Yes, that's good. I haven't used this lens in quite a while. I'll need to polish it. Anyway, that's fine. Let's hook up the... wow, okay. The extra camera, but I need to do it slightly further away. No, let's not do that. Pink is near yellow. What? No. There. Lock this down. Still not locked down. There, it's better. And now I need this power cord. And I need this HDMI. This is all so well prepared. I forgot that I needed this camera. Micro HDMI. It sucks. But it's in. good. Now let's see if we can target the power meter there. Of course, I can't see where I'm targeting. One moment, please. Okay, let's get this out of the way. This goes here, this goes here. I need to enable another view. Not that one. This one? Yes. Good. Good, we're getting somewhere. Okay, that's the speaker. Oh. Okay, let's lock that down a little bit. There. And now let's go to the big view. There. Now you can see the watts in real time like I'm seeing. Oh, this is a RGB CCT strip. So it has, let me show you. It has a red diode, a green diode, and a blue diode, and those are all in the middle section. And then it has a white diode, but it has two, so I can do warm white or cold white. Yeah, and it does that correctly now. If you configure WLED correctly with analog strips, that does work. Oh wow, these are already getting warm. Oh no, my antenna came loose. Oh, this antenna connection, I don't know, man. It really, really sucks. There. So, yeah, warm white, cold white. Yeah, of course, it doesn't have connection to the network now because the antenna disconnected. So let's reboot it. In theory, it should go to orange. Is that not the reboot button? Oh, there. Okay, there it goes. Okay. Who needs to be prepared if you can entertain us with the preparation? Isn't that right? So let's do blue. Oh, speaking of preparation, there's more stuff I need to do. I want to charge this guy. How much charge does it have left? Uh-oh. Oh wait, wrong side. No charge, of course. That is so stupid. Where is that plug? Over here? Yes. Of course it doesn't fit. Oh, such annoyance. Okay, that's charging. That's good. I have my other thermal camera, so that's not a problem. Yeah, but this is one of those 5-in-1 analog strips, and I'm going to try and show you without disconnecting the antenna again. There. So let's tone that down a little bit. So it has a middle part which has the red, the green, and the blue. And then if you set it to white, it has two whites. It has the warm white and the cold white over there. See that? And the phone melts. No, not yet, not yet. So I actually like this kind of strip because for RGB it's pretty good because those RGB diodes are pretty close together. And then it has dedicated whites. It's actually what is in the backlighting of my case over there. The whites aren't great CRI, but you know, it'll do for colors at least. So yeah, let's see if we can do some effects, right? because it's probably not going to work. Well, candle kind of works. It kind of flickers. Chase is not going to do anything because we only have 1 pixel. Colorful. Well, okay. I guess that works. Color twinkles, again, it's going to do stuff. But, you know, there's only 1 pixel because the whole strip is a single pixel. Color waves, same thing. Dynamic. Oh, wow. Okay. Dynamic smooth. Oh. Yeah, a lot of these are going to be nonsense. Fireworks starburst. But there's only 1 pixel. It doesn't work. Flow. Well, flow, you know. It works. Anyway, this is kind of nonsense. I was playing with this last night to see if WLED would run well enough on my AN Mini, which uses an ESP32C3. So that makes it special. Because I know it works fine on a normal ESP32 like the big boards use, but the small one uses a C3 because it's cheaper, and this one's meant to be as cheap as possible. Well, antenna came off again. That sucks. So, how was everyone's weekend? And I need to select a drink. I'm feeling Fanta Exotic. Does anyone have a suggestion for a label? I mean, there's not a lot of people here. So you make a good chance to select the label you want. Oh, thank you, M87. Looks like you're wearing your heart on your sleeve. What? Oh! After, like that? Yeah. It's a new thing in the chat. What kind of label do we want? Yeah, the overlay doesn't... Oh, it does work. I saw the hearts. No, it only works with the hearts then? I can't do it myself because on my side it's gone. Nice, the hearts work, but the others then don't work. Hey there, Nicholas Rutledge. Yep, doing fine. Oh, no, now all the emoticon thingies work. That's nice. That's cool. For some reason, I can't select them myself, but okay. You guys can. No. I'm feeling Fanta Exotic. So what label needs to go on here? I know it. Oh, Melt Plus. There. This is now a Fanta Exotic Melt Plus edition because I feel I'm melting already. So let's go. There. Here we go. The Melt Plus edition. Okay. Let's put it on there because I'm thirsty. Okay. Let's hope it doesn't wrap around. It does. No, it doesn't. Okay, good. There. The Fanta Exotic Melt Plus edition. Oh, nice. It's all wet because of condensation. Okay. Would it be cool if you string together multiple analog strips in WLED and create effects? Sure, you can do that, but the problem is with analog, each channel is a single color. So if you have RGB CCT, like over here, you're using 5 channels. So you could do 5 times white and then maybe make an effect with that. But it's just, less useful for effects. Ah, good. I like it. Okay, let's turn that off. disconnect the power supply because we're not going to use it anymore right now. Oh my god. Why is it so stuck? Okay. Oh, you guys couldn't see because I only had the overlay over here. That's okay. We'll return to that in a minute. Let me break down my current testing setup to build a new one, because that's what we're going to be using today. All right, as I was explaining, I guess I could easily show you. So with analog, each color has its own wire. So you have positive, cold white, warm white, blue, green, and red. And each has its own wire. So this is a 5-channel controller. So if you wanted to use more pixels or wanted to have, more addressable, you could move to one of the bigger ones I have over here, which, I'm also working on. And that actually has 15 channels, so 3 times 5. So then if you had RGB CCT, you could do 3 pixels. Or if you have RGB, well, let's see, that's 15 divided by 3. You could do 5 pixels. Whoa. Yeah, so real effects like that, you could have 15 white strips, and then you could start making some nice patterns over those. But then you only have a single color. So, it really depends on what you're going for. Now, I'm going to disconnect this 24-volt power supply I had in there just now, because we're not going to use that. And we're also not going to use this 24-volt strip, because we're going to switch to 12-volt. Basically, all LED strips I'm using, especially analog, have switched to 24-volt, but I do still have a large amount of 12-volt strip. So we're going to abuse that today, partly because if we're doing load testing, well, 12-volt will have the double load as 24-volt, because it has double the amps for the same amount of power. Okay, so we're going to put the analogs. This is also the 24-volt RGB CCT strip back on its roll, and we're going to abuse some older 12-volt strip, because I also have this LRS 600-12, which is 50 amps of 12-volt. We shouldn't be able to heat stuff up with that. And then if we know it works at, 20 or 30 amps 12-volt, it'll also work at 20 or 30 amps 24-volt. Yeah, it is. It is from the chat. That's new. It actually works. If you hit it in your chat, it'll show up over there. It seems none of my admins have been able to make it tonight. What's going on here? So sad. So I think I am going to use the AN Mini. So I need this block. Do I have another one here? No. Yes. Okay. So let's hook up the AN Mini to 12 volt instead of 24 volt, which we just had. Now I'm going to use some of this 10 gauge cable. Let me show you. It's 10 gauge, as you can see right over here. 10 gauge. Well, we only need one for the Mini. Now, for the Mini, with the Mini, we're not going to be melting LED strip, in theory. Maybe we will. But for this, I want to test the maximum output current each of the channels can sustain before it basically gets too hot or higher than I'd like it to be, right? So we're going to jank this in there, because this kind of terminal isn't made for forks. But if you do it like this, it does actually work. I'll show you in a minute. I have to make sure that's properly in there. So now the fork sticks out on this side, And from this one, it sticks out on the other side, so they're not touching. And I'm still able to use, there, that's nice and tight, 10 gauge cable without it touching, right? And it can't really touch because there's the installation there. Okay, so we need to hook up the other side to the power supply. Let's plug this in. It's still turned off, so that's fine. And let's wire up the power supply. So here's the power supply. And this, as I said, this is a LRS 600-12, and it has 12 volt 50 amp output. Now this board has two 5 amp fuses, auto reset fuses, as you can see over here. So the max we'll be able to use is 10 amps, but still it'll be a good test to where did I put my screwdriver? Oh, here. To determine the maximum per channel, basically. So, I really love fork terminals. Actually, some of the analog products are slightly delayed because I really want fork terminals on there. And it's really hard to get fork terminals into a case. But anyway, it is what it is. Okay, let's do this like so. Kind of like it this way. Okay. Now, for LED strips, I have a bunch of old 12 volt LED strips, as I mentioned. And I have no clue what they use in regards to power. There's nothing on there except this sticker indicating that it's some kind of white. It's probably horrible. And this is like, well, it's not 10 years old, but close to it, I think. So let's just wire it up and see what it does. Okay, that's open, that's good. And let's wire it up to this channel over here. So the way the AN Mini works, it has two positive output channels, that's these two, and then it has 5 negative output channels, so that's basically your colors. 2 of those are level shifted, not the 10 volt, but the 5 volt, and 3 of those are run directly off of the ESP. Turns out to be, no, it says 12 volt right on here. Let's see where it can, yeah. Let's see here, 12 volt, right? And this just gives us a bit of time for the thermal camera to charge. So this is 12 volt. This is positive minus. Yeah. Okay, let's go. Oh no, wait. I still need that janky antenna. I really don't like this antenna, but I need it. Let's zoom out a little bit. Nope. There. Now, most melt testing will do with the bigger boards because those can handle up to 10 amps per channel. These, I think I'm going to spec them at like 4 amps, maybe 5 amps per channel for the level shifted channels or the gate driven channels, and these probably 3 amps a piece. But if you're driving RGB, CCT or whatever, you're not going to be nowhere near that. So this going to the strip, I don't know what it is. Let's see. It does say something. I don't know what kind of gauge it is, but the wire is so short, it doesn't really matter. I just thought of something. I'm so annoyed by this antenna. I'm just gonna stick it down. There! That fixed it. Now it should stay down. Oh my god. Okay. There. Antenna secure. Let's turn on the power. Okay, let me Oh wow, it's drawing 8 watts? Of what? Uh-oh. Oh, that's probably just because of the bigger, less efficient power supply. Let's see if I can refresh WLED. I can. But of course now, it's only connected to this channel, and we don't have RGB CCT anymore. So we need to set it to white. Okay, something came on, and then, is it this white? No, it's the other white. There. Let's see the maximum power we can draw here. 39.4 watts. That's probably going to be toasty really quickly. I guess we want to know the amps that are coming out of the wires here. I need to get my amp meter real quick. Hold up. Okay, I'm back. So let's separate these wires. And we have our amp meter. Let's zero it. I guess I should turn on the light. Does that work? Yeah. It's not very clear, but... Okay, there. I was already worried about the antenna, but I stuck it down. Okay, we're doing 0.26 amps. That's probably correct. Let's move it up. 1. Okay, full power. Oh, it's only 2.4 amps. Yep, it's only 2.5 amps. That's not a lot. I do hope I have better strip in here. Or, you know, strip that uses more power. Let's see what happens if we just add more, you know. So this was about 2.5. Let's tone that down a little bit. And let's just add more. Because we're in the end, I'm mostly interested in the temperature of the MOSFET to see if this design works as intended and it doesn't, you know, heat up uncontrollably. So I'm just going to stick it into the same positive terminal here. Now normally I don't think I'd advise that, I guess, I don't know. And the same negative terminal. There. So now it's like, oh, this is already getting, wow, this is so hot. Okay. A preparation thing I also didn't do was put my silicone mat down. So we'll do that right now. Wait. Oh, there it is. Because if we're going to be melting stuff today, well, it's best on the silicone mat. Then it won't melt my desk mat. You know. This is already feeling toasty. And that's exactly why you shouldn't run this on, you know, while it's still on the spindle. So let's max this out. That is... well, let's say 70 watts on the power supply. And now... oh, wait. No. Need to start the meter. Zero it out. There. So this strip is now using 2.46, okay, and the other one is using 2.3, 2.4-ish, okay? So together, that is about, let's say, 5 amps. Can I measure it together? I think so. Yeah, I can. Nice. So that's about 4.9 amps. That's actually right on the money, because this automatic fuse is 5 amps. Yeah, I know stuff is going to melt today, so better be prepared. Now, can anyone tell me why this is creeping up? It has a reason. Yeah, heat is actually the right answer. When this is heating up, and this one too, the resistance actually decreases. And when the resistance decreases, it starts to draw more power. And this is also kind of when you know something is saturated, or it's reached a steady level, if it isn't increasing in power anymore. Because if it's still increasing in power, it's likely still heating up. And, well, this is already quite warm. Let's see if our phone has enough juice to boot. Let me take that over here real quick. We'll just leave this running. It's only drawing 5 amps, as we saw. So, 4 point something. It's actually dangerously close to the limit of this this PTC, which is also heating up. The PTC actually does work in reverse, though. The more it heats up, the higher resistance it becomes. Most normal electronics work like, if it's hotter, it has a lot less resistance, like a cable or an LED strip, etc. But a PTC works in reverse. That's why it works. Oh, we're beyond 5 amps, so in theory, this will start limiting at some point. Not yet, no fire yet. Oh, okay. The phone is already at 30 something percent, so that's good. Let's see. Where's my measuring app? Okay, so let's change this real quick to RGB. Okay, how warm is this stuff? Oh, wow, why is it so slow? I don't know. I'm seeing readings up to 120 degrees, is that right? Oh, okay, well, it is really hot. Not sure that's right. Let's see if I can calibrate it. Calibration successful, okay. So I'm going to remove the clamp meter right now. Oh, Philip is here. Oh, I am already starting to smell some burny, melty stuff. Let's see here. Yes. I don't know if you can see on the screen, but parts of it are actually... oh, that's why I'm having a hard time seeing it. There. I should do it like that. Parts of it... Oh, no, now I need a different color, because this sucks. There, that... I guess. I don't know. Let's do this, because then you can actually see the red letters. Parts of it are 143 degrees. Switching radiometric range? What? That's new. Yeah, well, this is just, two simple strips. It's only drawing 5 amps, but it's already at 143 degrees. Which is quite a lot. And the other one is at 132 degrees. So that immediately shows you why you shouldn't run LED strip on the roll. Ow. Oh wow, it's already starting to deform. Can you see this bulge here? But I was mostly interested in to see how the board was doing. But now it won't show it anymore because it's... Oh, switching radiometric range. So the MOSFET that's driving these 5 amps is currently 50 degrees. 48, 47. Yeah, that's fine. And then the PTC that is currently regulating this is at 60, 65 degrees. Yep, that's fine too. If it trips, it'll be over 100 degrees. So, yeah. So, the board, which is one of the tests we were doing, one of these channels can easily drive 5 amps output. Because, well, it's doing that right now. We measured that. And the MOSFET isn't even 50 degrees C. Yeah, this is... It's not rising in temperature anymore, but I'm measuring 151 C here. And exactly, Brent, this is the reason we don't test LEDs while they're still on the spool. Because we've only been going for a few minutes. I'm glad Philip is here. But, oh yeah, let me show you this. And I can smell it. Can you see that? It didn't start like that. Can you see it over here? How it's bent open and this is curling up like that? That is actually the spool melting. Yeah, if these were done with low temperature solder like I use on my prototypes, it would be desoldering the LEDs right now for sure. Because we're seeing 150 something over here. Meanwhile, board is like, I don't know what you're talking about, man. It can't measure it because it's below 80. Come on, switch range or something. Okay, it doesn't want to switch range, fine. Well, I do actually want to measure that, because that was one of the tests. So let's look over here for a little bit, I guess. Okay, switching radiometric range. Okay, now let's look at the board. This MOSFET... Oh, okay, it heated up a little bit. MOSFET is at 53 degrees. 51, 50, 50.6. Well, let's call that 50 degrees, okay? Yeah. And the PDC is at 60, 67. Okay, so let's turn that off real quick. Power. Okay, and now let's move from this output channel, which is on the level shifted MOSFET, to one of the... oh man, plastic smells big here. To one of the non-level shifted MOSFETs. Because in theory, that will run higher because it's not getting 5 volts as this one is getting, but it's only getting 3.3 volts directly from the ESP. So let's see if I can get both these wires in here. I should be able to, I think. Wow, this mat is hot. Okay, that's connected. Wow, oh, everything is hot. think the controller is actually heating up because this is so hot. Look at what happened to this. Ow, ow, Ellie, ow, ow, ow. That certainly wasn't the way how it started. Can you see what happened there? Yeah, that literally melted that roll. Ow, 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 ow. It's hot. Okay, fine. Yeah, so now we're going to test the other output channel to see how that does. So if I now turn the power on, nothing happens. That's because we need to find the color it's connected to. So it's no, it's not connected to red. It's not connected to blue. It is connected to green. Okay, we're at 71.4 again. On the left spool on the outside ring. What figure? Oh, thanks there, Von Tolkien. So we're again drawing 71.5 watts. That's actually good. That means that my circuitry and the MOSFETs and everything I'm using works correctly. Because we're again drawing 5 amps. We'll measure that real quick. But this is a MOSFET that isn't that doesn't have a dedicated gate driver in front of it, but it still gets the same output, but it'll likely run hotter doing so. Silicone LED spools. No, you just shouldn't do this. Yeah, I'm also a bit surprised the outside gets the hottest, but it could also be because this is so tightly wound that it just can't measure it. Or because the heat is actually soaking outward because it doesn't have anywhere else to go and it's all connected together. So, yeah. Right, so let's see here. Okay, this MOSFET is already 57 degrees, 56. So it's already hotter than the other one ever got. But that's because the gate voltage is lower because it's being driven from the ESP and not with 5 volts from the gate driver, basically. Right? Well, yeah, this will be the same temperature here. Oh, switching radiometric range. So 145 and 130. Let's make it even worse. Let's put them on top of each other. See if I can measure. Oh, ow, 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 that's hot. 131. Oh, the lower one is 147, 148. Can you see those numbers on the stream? On the stream? You saw it flickering? What do you mean flickering? Like on fire? Burn, baby, burn. Okay, let's hope it switches back because I want to read the MOSFET again. That's the real test today. To see how much output power I can use per channel. Oh, my meter's beeping. Okay, so this MOSFET is now getting 60 degrees. $55. Oh, it's probably one of the LEDs losing its solder joint. So let's get this on the screen a little bit more. Right, so in the end product, I'm probably going to rate these 3 channels to 3 amps each, and then these 2 channels to 4 or 5 amps each. And then we'll be perfectly well in temperature range, I think. 60 degrees isn't too hot, so you could run these with 5 amps, but then if you're going to run 3 channels, yeah, I know, those are going to be close together, so that's going to heat up even more. And the board itself will be limited to 10 amps in total, partly because of the input terminal, because that will also get hot at some point. It's not right now, but yeah. So having a gate driver to 5 volts there, instead of doing it directly from the ESP32, seems to make about 10 degrees difference. Okay, that's interesting. That's good to know. That kind of means that the values I set out to achieve, I think I'm peaking sometime there. The values I set out to achieve for this board, seems to be doing very nicely. Because, as I said, we have 2 times 5 amps available on these 2 fuses, which are these 2 output channels. And then you can use them for 2 high power channels, or a mix of low and high power, etc., up to 10 amps max. Mainly a cost reason there, Philip, and slightly board space. I guess I could have made it fit, just change the design, but mostly cost. This one is built down to a cost, so yeah, this one I'm trying to get as cheap as possible, but still do the function perfectly. And if you're using RGB CCT strip like I had on there before in 24 volt, we're still talking 240 watts of power, so you can run multiple of those strips. I switched to 12 volt especially to get higher amps to test out load. And if you need more than that, well, then there's the other board. So yeah, I have seen LEDs videos by Chris Maher. I have some thoughts about that mighty anus. I actually responded to you on your question on my latest YouTube video, so you should know my response to that. And otherwise, I suggest you check it out there, because I responded to your comment on my video. Now, I am going to... oh no, it's melted together. Oh no, can you see that? It's actually stretchy melting together. Okay. Stop it. Where's the stop button there? Grab a sandwich. Okay. So, yeah, this is now gone to the point where it's actually melted together. So yeah, this is, I think, a very good showcase. Ow. Why you shouldn't run LED strip on the roll. Ow. Look at how bendy this is. Ow. Okay. I'm gonna stop touching it for a while. So, okay, now we saw 5 amps on this board and 2 different MOSFET configurations, right? Now let's do the same, but on my bigger board, and we're also going to try and load that board up. So let's disconnect this. No, that's why I put it on this mat. This is silicone mat, and that shouldn't burn until it's like 200 or 250 degrees or something like that. And that's why that mat is there. Okay, let's get... is it this one or another one? I don't remember. Does it matter? Let's see. No, I don't think it matters, but let's take this one. Okay, let's take our power cord here. It's turned off, good. Now, as you can see, this board has a very nice beefy input terminal. They got brown? No, I don't think so, but... Okay. So this board, this is the, well, it says it right here, the AN Hybrid Hexa. This one is meant when you want to use very high power strips. So in its design, each MOSFET should be able to handle about 10 amps. So that's double from what we just did. So let's first see what it does with the same amount. And this one also has different gate drivers. This one has single gate drivers, so there's a gate driver per MOSFET, while the AN Mini has a single dual gate driver for those two high power channels. Yeah, the LED strips were having a hard time. Maybe I should get them off the roll, I don't know. I'm putting them on the roll again, what's left of the roll. Because there's not much left of the roll. Why is this LED... Okay. I need terminals. Oh, maybe I use this one last, because this one has terminals on it. Yeah, so let's use that one. Okay. Yeah, even in the first test where I wasn't intending to prove it, it's definitely proven. Wow, there is a hot air balloon that's almost at the height of our house. Oh my, that's quite low. I hope it's going up, because otherwise it's really going to crash into something. Sorry, I have to keep an eye on that. I don't want the hot air balloon to crash into our house. I think it's rising. Hot air balloon stalkers, they found me. Oh no. Okay, it's past the house, so it's not my problem anymore. Okay, let's give this one Ethernet. There. And let's hook up the same test, right? So we're going to use a single positive channel. This one has 4 positive channels instead of 2, and each one is fused at 7.5 amps instead of the 5 amps of the other one. I'm gonna try and roll this up, but this one is really, yeah. Okay. I need to see how I'm gonna do this because I don't want my cable to melt. I guess something like this. Yeah. Yeah, I'm not sure if it's actually landing or going up. But it's past the house now, so it should be fine. And there are some fields near here, so I guess I could touch down there. Go in there. Yeah. Okay. No, these are actually garbage strip because they're old, very old 12-volt low CRI crap that I'm not going to use anymore. So I don't mind them burning a bit. That's fine. Right, let's see if we can get this board online. This one should be in ESP Home. Do I have that connected correctly? I think so. Yeah, we have an orange LED for 3.3 volt and a green LED for 10 volt, because these are all gate driven with 10 volt MOSFET gate drivers, a single one. And we have Ethernet here. I guess you can't see. It's okay. Now I need to see if I can find these. In theory, this is the hybrid Hexa 2, maybe? Let's see if it got an IP, but it probably has a static IP. Oh no, it doesn't. 106. There, it is online. Oh, yeah, it's online in Home Assistant. Nice. Don't need to do any ESP Home crap. Okay, let me zoom that in for you. There. So this is probably this channel? Yes. Okay. Now, in theory, we'll see about the same power usage, because 100% here is the same as 100% on the other board, but we see a slightly higher number. Oh, wait. That's probably because this MOSFET configuration is actually slightly better than on the AN Mini because of the 10 volt MOSFET gates, and there's more expensive, better MOSFETs on here, and blah, blah, blah. Better terminals, and better tracks, and more layers, and things like that. So that's probably why we're seeing slightly higher output, but not by that much. So where the other one was like 12.91 volts on the output, this will be 12 or 11.91. This will be 11.94 or something like that. Okay. Well, that's running. That's good, I guess. Now what? All right, we're gonna leave this soaking for a little bit to see how warm this MOSFET over here. You can't see it. This MOSFET over here becomes, and then we're going to hook up more, because we're going to test this one to 10 amps. Now it's going to be kind of hard to prove how much it can handle, because it'll be partially dependent on the frequency you're going to be running. Currently, this is running PWM at around 20 kilohertz. But if you wanted to say run PWM around 120 kilohertz, the MOSFET would become less efficient because you're switching it on and off much more each second. So it's going to waste more in heat. So I'll probably pick like 1 kilohertz, 20 kilohertz, and then 50 and 120 or something like that. And I'll list amperage numbers that I recommend per MOSFET per frequency, because otherwise it's very hard to judge. Normally you buy a product and it's like a set frequency, so it can do that. And especially those products are like 100, 200, 400, maybe 1000 hertz, and then it's easily to do all those amps. But if you want to do the same amount of amps at 50 kilohertz, yeah, it becomes much less efficient, and you need to do much more elaborate design. Okay, well, this is getting nice and toasty. I don't know if it's oh, wrong way around. Yeah, getting brown there. I haven't really seen it. It could be because it's burning, basically. More melty, yes. So let's first see the MOSFET, if we can find it. Yeah, it's maybe 34 degrees. 38, 37. So as I said, this is a much better setup, so the MOSFET will get a lot less warm, basically. But it's also more expensive, you know, so 36, yeah, this MOSFET's not carrying. Now, this one has two 3.75 PTCs, so together that makes for 7.5 amps. and they're currently running at 46 and 44. That's fine. Meanwhile, the LED strip is melting. Yep, 123. Well, the Mini is actually also 4-layer. But yeah, there's more surface area here. And on this one, the outer layers are 2 OZ, while the inner layers are 1 OZ. And on the other one, it's all 1 OZ. So yeah, there are some cost aspects there. This one's 155 degrees. I'm trying to get them out, Mark. But I've been saying 2 months, but it's probably going to be another 2 months because we've run into some issues with the prototype boards, which we actually saw on the live stream last week, the last live stream. We're getting those fixed and then sent out to the testers because I still want them to test the boards even with known limitations. And we've run into some issues in regarding to the case because I really like this barrier style connection, but integrating that into a case is much harder than a pluggable style connection like this. And I have those for 30 amps, but the problem is that those are like $2 or $3 a piece. So that's going to change the whole cost perspective of the board, and you still can't use fork terminals and things like that. So damn USB. The USB is right here. It's burnt. This chip is probably burning. Oh no, this is one we burnt off last week already. Oh no, I can't measure anymore because it's in different mode. Come on, switch. Okay. Yeah, this MOSFET really isn't caring. It's like 38 degrees, 37. So 5 amps, let's measure it for just to be sure. But 5 amps on this MOSFET is easy living. It doesn't care. Okay, let's zero this one. Let's clamp it just to be sure what it's actually doing. It's currently doing 5.4 amps. The red heart is because the YouTube chat is updated with a feature. On your screen, you should also be seeing a heart in the chat, and now you can spam a heart or other icons on the chat overlay. Indirect or direct, yep, that's basically what it is. So if you don't need effects or you want good quality white light, you'd use analog. Yep, there we go. There goes the hearts and the smileys. So 5 amps, 0 problems, right? So I'll just turn the channel off. There. Pew. Oh, nice fade. Okay. Let's hook up more. Because that's the way of the game. Okay, I'm going to snip these off. There we go. I think, what was he called over here? Grab a Sandwich found my comment. I wrote him a really decent, good, long reply, and he didn't even look at it. Jesus. Anyway, what we're going to do to add more current is we're going to use a second output channel, because each of these is limited to 7.5 amps. And then we're going to use the second terminal over here. And these are made to run high power LED strip. For instance, if you run one of those Oxmoor 28.8 watt per meter LED strips, you're going to need to power inject at some point. So each single MOSFET here has a double output from the same MOSFET. That's to do power injection. This one has that too. And then here you have 3 RGB channels again. So you'll be limited in current a little bit versus these, right? But they do still have the same level drivers and things like that. Oh no, it's all the way on the inside. Well, that's what it is. And oh, I have a fourth one. Nice. Oh no, this one doesn't have any ferrules. Oh, okay. We're gonna melt some more LED strip. So let me prepare these wires real quick. I need to split them anyway. Now there's two ways to run this. One is set to 100% like we just did. But we're also going to test it PWMing. Because if it's set to 100%, that MOSFET can handle a different rating than when it's actually having to PWM. Because then it's having to switch on and off rapidly. Well, if it's just on, well, it's just on, right? So let me wrap this around here and then try and get that in here. That didn't work. Okay, this one goes in first then, I guess. And then this one. Yes, that should work. Yeah, funnily enough, this LRS 612, it hasn't even turned on its fan yet. Okay, that's in there, that's good. And then let's use the second terminal here. So we had about 5.5 amps just now with the two strips. So adding another two, we should get at least 10. A little bit more probably. There. Let's see if that's... No, see, that's not secure. Okay. Nope, still not secure. Damn it. Am I going to have to put a ferrule on there? Now I'm actually screwing into these terminals while the board is turned on, but because it's MOSFET, this port is effectively really turned off, so that shouldn't be an issue. Let's try and get it as tight as I can. Nope, still able to pull it out. Okay. Let's try and wrap it around there like we did on the other gun. There. That should hold. Yeah, there's a bit less people here, and some are chatty, some aren't. That's fine. Okay, now we've got them connected. Good. Let's see if we can cook these. The board isn't that interesting. Oh wow, the mat's still hot. Oh no, these are like fully stuck together now. Okay. Well, as I said, this is old crappy 12-volt strip, so it doesn't matter. Okay, well, let's turn it on. Yep, that works. Okay, we're now at 100, let's say 130 watts. That's good. Let's get the clamp meter out. Let's zero that. Okay. And now we need to measure all the positive wires. See if I can do that. I think so. There. Oh, we're almost there. 9.9. Whoa. I'll call this close enough to 10 amps. Modern Quinled art, yes. Well, okay, there, 10 amps, right? We got it. Still heating up. So I did have to divide this over two output ports because each of these output ports will only do 7.5 amps because of the auto reset fuses. But having 4 of those, that still means you have 7.5, 15, and in total 30 amps, which is the board limit anyway. So yeah, that shouldn't be a problem. I'm trying to arrange this somehow. Okay, let's measure the temperatures. Where is my phone? Get it hot enough so you can separate it again. Yeah. No, it's not that bright because it's still on the roll. So all the energy is being projected into... Whoa, this one's having not a great time. This one's starting to flicker. That's probably what Philip saw earlier too. Yeah, those are dead. Okay, so we have a little hotspot over here, which is the Ethernet chip. That's normal. There's a regulator in there. And it's running about 45 degrees. That's fine. That's perfectly fine. Now we see that more PTCs are being used because we're using 2 output channels, but we have 7.5 amps on each, so 15, and we're only using about 10. And now let's see, the MOSFET is... It's 43 degrees. Yep, that's not hot. So it's now doing double the amps as the AN Mini on the single port, and it's still 10 degrees cooler. Yeah. So let's see over here. 70 degrees on the strip. 140. Oh wait, you can't see. Oh, it's needing to switch radiometric range. 125, 146, 150. Yeah, it's LED strip be hot. Okay, well, let's leave that running for a little bit. So I can get a drink. While smelling these beautiful plastic fumes, right? I think that calls for some Fanta Lemon. What? We already had the Fanta Exotic Melt Plus edition. What is our Fanta Lemon going to be? Barbecue? Fanta Lemon Barbecue? What kind of label do we need? Toasty, Fanta Lemon Toasty. LED beefer, what? Fanta Spicy Lemon because it's hot? Oh, whoa. Things are smoking. Can you see that? What's smoking? Something is smoking. Yep, there's smoke. Definitely smoke. So I didn't disappoint again. Oh, whoa, whoa, whoa. This one's above 170 degrees. Oh wow, it's at 192. And 195, 192. Yeah, there's definitely smoke here. Oh my god. Okay, I'm gonna stop it. Sorry. We're going into... Oh no, I need to still measure the MOSFET temperature. Hold on, just a second. Let's see what the MOSFET is. Come on. Okay, the MOSFET is still only 46, 47 degrees. right? Okay, that's fine, that's fine. Okay, let's lower the power to 50%. Well, this can only have one name now. Do you guys know what kind of name this Fanta now is going to be? The Fanta Lemon Smoked Edition. Because what else? This is bad for your health. Yeah, it kind of tastes like that. So let's enjoy some Fanta Lemon Smoked Edition. There. Fanta Lemon Smoked Edition. It's bad for the LEDs, really. Oh, is this now... Oh, ow, 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 ow! Okay, yes, this is now melted together, yes. I'm gonna open a door real quick, just to vent the place. Hold on. Whoa. The whole garage is smelling like smoke, like molten plastic smoke. It's a lot more than I thought, actually. Yeah, you're donating to my lung cancer fund? No, the fire extinguisher is right here. See? It's fire stop. There. Fire stop. No problem. It'll stop any fire. I need a drink. Thank you, Brent and Philip, for the donations for the extra smoke. Well, it's not 20 years old. It is over the date, though. Okay, we've been running this MOSFET at about 50% for a while now. Let's see what temperature the MOSFET is now. Oh. It's still... Let me try and show you. It's still only 42, 43 degrees. But one of the caps has heated up though, but that's normal. So one of the things I did on this design, which most other analog PWM dimmers don't have out there, is I have a capacitor per positive output right at the output. I also have a lot of on the inputs, but right at the output. So that normally when you're PWMing, you're basically turning on and off the power to the LEDs real quick. And you're doing that on the negative side. But of course, when the negative is gone, the positive also gets a hit like that. So my idea is having all that brunt or switching on and off handled by the power supply. That also means it has to travel over all the power cables and through the board, etc, etc, etc. So to try and smooth that out as much as possible, each positive output has its own output capacitor locally, so that that PWMing basically happens in this capacitor, and that the currents flowing through the board and especially to the power supply are as smooth as possible. And that also means that PWM noise from your power supply is basically effectively reduced or non-existent. Because we've been running from this LRS 600-12 for a while now, and we've heard zero PWM noise anywhere. And that's, you know, because of the board design. Okay, now I'm not dying of smoke anymore. Let's see what the MOSFET is. Well, unsurprisingly, it's still 40-something degrees. Okay, so let's up that to, I don't know, 70, 80%. There, 80%. Nice and smooth fade. Oh, I love those smooth fades of analog LEDs. Stop sales pitching and release it already. Yeah, I know, but I'm still doing testing, Philip. I need to test this stuff before it gets released, you know. Yeah, testing is kind of boring, though, because now we wait. So we've set it to 80% now. Live dangerous and release version 0.1 with blowing up USB ports? I don't know about that. That's already been corrected, though, but... Okay, even though we're pumping a lot more amps through it now, it's still only drawing 40... It's only 42C. 46. Yep, that's perfectly fine. So, how about we change the code? Because at 20 kilohertz with this kind of load, it's perfectly fine. Free magic smoke in the package. Yeah, I don't know about that. So let's measure how many amps this actually is. Oh, okay, that's perfect. We're doing 5 point little bit amps, right? Okay, so let's change the code to run at 120 kilohertz instead of 20 kilohertz, and see what kind of difference that makes in regards to the heat on the MOSFET. So let's go to ESP Home. I'm probably going to be sharing passwords again. Who knows? But they're all test environment passwords anyway. And it's... which one is it? Oh, it's saying offline. That's not good. This was the AN Hybrid 2, right? Yeah, AN Hybrid 2. Let's see if I can get logs. Oh, I can get logs. Okay, then I can update it. That's fine. Yeah, so it's currently at 19531, so that's about 20 kilohertz. Let's go to... Well, I need to multiply that to make sure it's in the right PWM range. Times 2, times 2, times 2. Oh, that's a lot more, wait. No, 19531 times 4? No, times 6. Yeah, 1171. Okay. 117186. And this has to do with how the ESP handles PWM and the available steps, basically. That's why you don't pick the totally full number, but you do it like that. So let's install that wirelessly via the network. Ow! Okay. Okay, I was wondering if they were hot. They are hot! Damn! Okay, uploading. Okay, and it's off, so let's switch it on. So running it at 100% shouldn't make a difference at all, but let's go back to 50%. Okay, so it's not running. These are now stuck together too. And these are like permanently fused. Okay, let's run it at 120 kilohertz right now at 50% for a little while and see what happens. The banana principle, let the project mature to the consumer's home? No. I will keep improving products. So there's been new versions of the Dig Uno and Dig Quad and etc. and the ESP32 recently. But if I can improve and make it better for the same price and keep the same functionality or more, I'll try and do that. So I think that's valid. But the initial product you release should be good at what you say it'll do. Don't make the customers pay for something that doesn't work. Hey there, Henrik Eckhart. So let's see if this heats up other stuff on the board. I actually don't know on this one. Okay. Oh, see that? The MOSFET is now 50 degrees. Isn't that the viral LED business plan? No, the viral LED business plan is even worse. It's, let's take something that's crap, and everyone knows not to do it, put a housing on it so they can't see we're doing it anymore, and then sell it for 10 times as much money. When Quinled OG V2? I don't think there's going to be a 2-channel board. The AN Mini is 5-channel. That's going to be the smallest one, I think. But I am working on some interesting projects there, events, CJ, but you know that. Or brainstorming, at least. So even though we're running at 50% again, and we're actually getting slightly lower light output, the MOSFET is now 50 degrees because we upped the frequency range, right? Or the frequency it's running at. Still, 50 degrees is perfectly fine. And this is only drawing a few amps probably. Let's see. Need this wire too. There. It's drawing 1.59 amps. Okay. Let's go back to 80%. So that's right around 5 amps, just like before. That's good. And let's see how hot this MOSFET gets. Because as I said, at 1000 Hertz, 20,000 Hertz, or 120,000 Hertz, it'll have different current ratings, basically. Oh, these can run officially like 100 amps. But it all depends on how you drive them, how they're heat sinked, PWM frequency, things like that. Hey there, Mr. Tech Gadget. Enjoying this public testing session. Cool. Well, glad you like it. I like showing how things really are. I mean, last time we learned that I can also make board mistakes. Okay, let's see how hot it's getting now. Oh. Well, it's not an uh-oh. We're at 56 degrees. That's fine. 59, 58. So that's now about 15 degrees warmer than we were running at 20 kilohertz. Now there is multiple reasons for that. One of them is that I've tuned the outputs So there's resistors in the output channels which will basically make the MOSFET less efficient. The reason to do that is if you make a very square pattern, that is of course digitally perfect, but for EMI and EMC, that's horrible. So it's radiating a lot of radiation, etc. If you were able to make a very smooth pattern, that would be very great for EMI and EMC, but then horrible for the MOSFET because it would be in the on or off state. It's basically efficient when it's off or on, and anything in between, it's less efficient. So it's burning energy. So if it looks like that, the MOSFET is very efficient and can handle tens of amps. But if you smooth it out really a lot, it'll only be able to handle maybe 2 or 3 amps because it's in that transition area a lot. So I kind of tuned this in the middle. It should be able to do 120 kilohertz because I think that's high enough. But above that, it'll start getting less efficient really quickly until it really can't even achieve the frequency anymore because it can't reach the top before it has to go down already, basically, of the PWM wave, basically. So that's why it's becoming less and less efficient, because I am basically limiting its performance to make sure it doesn't create a lot of EMI and EMC. Yes, I have experimented with that CJ, but in this product, for the amount of amps I spec it for, I basically just got a better MOSFET to not have to deal with heat sinking and things like that. So I could easily remove that resistor and remove all those limits and have it slam the gate with a few amps at 10 volt, and it would do 40-50 amps no problem without heating up. But then you're generating a lot of EMI and it's better to smooth that out if you want to actually make a product. So we've been at 80% for a little while now. Okay, we're at 61 degrees. 62. That is about my intended target. So even with 5 meters of 28.8 watt high power LED strip, you're still going to be able to run that with these values, basically. Yeah, you'd fail all kinds of ratings. I'm not even sure this one will pass. We'll have to see about that. Let's go to 93%. Probably going to start smoking again. Let's see how many amps we're doing. But it's always going to be a balance of having a smooth rate. Oh, okay, we're doing 7.8-ish, 7.9. Yeah. I've investigated that, Mr. Tech Gadget, and this is a 4-layer board with 2 OZ copper on the front and back. And it's heat sinked up to the wazoo, so having more area on the front isn't going to matter too much because there's internal planes that are spreading the heat out, basically. And that also has to do with EMI and EMC and how you want to put that on there, basically. So this is already very much heat sinked into the board. Because now probably the MOSFET is heating up to max, because it's having to turn off 7.5 amps or so 120 times a second, and I'm actually limiting its performance by those resistors so that it can't just make a straight edge, but it has to make smooth edges going up and down to reduce EMI. Still, we're at 66, 67 degrees. That's perfectly fine for this type of MOSFET. And you can see the area around it is also heating up, right? So this part of the board is now 52 degrees, and even over here it's 48 degrees. Over here it's 50 degrees, but over here it's only 40 degrees, right? 40 degrees, 40 degrees, 39 degrees. Here's the Ethernet again. The PTCs are heating up a little bit. Let's take a look at the back of the board. Well, here you can also see clearly that it's spreading out the heat. So over here it's 57, 58. Oh, the LED strips are smoking again. And here the board is 50 degrees, but over here, as you can see, the board is only 39, 38 degrees, etc. So it's really spreading out that heat inside of the board. 50, 50. Okay, yeah, smoke. So let's take one last reading. It is currently at, oh, you can see, 66 degrees. Yeah, I'll take it. Now I'll do, yeah, exactly. These MOSFETs can easily run 100 degrees if need be. But I'd rather design it to have it stay lower, if possible. But you just saw me setting all these channels to 120 kilohertz. We measured that even at 90-ish%, we were doing 7.5 amps. And the MOSFET was only getting 60, 65, or 65, 66 degrees. So that is perfectly within spec. So even if you wanted to run 120 kilohertz LEDs and you wanted to run a high power strip, that's no problem at all. And then this is just a single MOSFET. There is another one over here, which, you know, does the same. And then there's 3 other ones over here. But those 3 are closer together, so I advise those to have a lower limit than these 2, which are widely spaced apart and are very heat sinked, etc. They are, however, all gate driven and with the same amount of boards and same amount of heat sinking, etc., etc. But that is also why these 2 have a 2 output channel 2 output terminals per MOSFET to exactly do this. Have multiple strips or high power strips with power injection, no problem whatsoever. And then you still have some RGB and, you know. And again, this was about 10 amps on this MOSFET. If this one can do it, you saw that the heating was pretty localized. This one can do that too. And then you still have those 3 channels. And this board in total is rated at about 30 amps. So I believe you can actually use those amps even when running at a higher PWM frequency. Easily at 20 kilohertz and probably still at 120 kilohertz. But yeah, that took some engineering to get the MOSFET gate drivers and all the resistors and everything else tuned correctly to do those frequencies. We could, for instance, as a fun thing, say, okay, now we know that works. Let's go to 300 kilohertz. Because I believe this will not work. Well, it will work, but it will probably overheat. Your boards will outlast several replacements of LED strips. Yeah, probably. But that's the idea. I like making good hardware. I don't like making crap. I could make it a lot cheaper and have it run at 100 degrees plus and it'll work. It's just not something I like. Right, so now we're at 300 kilohertz. I don't have an oscilloscope. I do have an oscilloscope here, but it's not on the desk, so we're not going to look at that. Let's turn that on and set it to 90% again. So that's drawing 105 watts. That's fine. Now this MOSFET's likely going to heat up pretty quickly. Tune in your AM radio. Yeah. Oh, uh-oh. Yeah, it's already at 75, 77 degrees. Can you see that? It's at 80. No, because if it needs to heat up, it also needs the amps basically. Because if I turn it down, it'll probably be cooler. Let's see. Yeah, it immediately drops in temperature. See that? So now it's only 75. Let's go to 95%. Oh, it's still dropping in temperature. Why is it dropping in temperature? Ow, my finger is... My hand's burning. Go away. Okay, let's lower it to 80% then. Yeah, okay, spiking. Yeah, 70 degrees. Okay, 70%. There's probably some weirdness going on where at a certain point it won't reach the bottom anymore, so it'll just keep floating. Still, if it's not going above 70 degrees, that's not too bad actually. Let's go 60%. I don't know, let's go 25%. Well, now there's not a lot of amps going through there, so it's cooling down. I don't know, 95%. Whoop. It heats up, but then starts to cool down again. That's weird. So, 82. 70. 60. Well, if we can't get it to go above 70 degrees, that's not bad. $56. 64. Huh. Let's run it real low. Okay, that's too low. It won't be much worse in a case, I think. Yeah, we do need some margin, that's true. But also, currently it's flat on the table, so it's not getting any cooling on the backside. And in a case, it would be floating inside of the case, basically. So it would have some air on the bottom and on the top side. So that would actually make it more ideal for the board. But then again, it's a closed space, so yeah. Yeah, but I don't think we can find a value that's going to cause an issue here. But I'm not 100% sure the waveform at 300 kilohertz is going to be correct, because I tuned it for 120 hertz kilohertz and below. But I'll have to oscilloscope that. Maybe I took a value that 300 kilohertz was still fast enough. 1 gigahertz. Okay, well, no, we can play with it, because I'm gonna... This will be the end of the stream soon. We're going to go 600 kilohertz. And I know nothing is tuned for that. Let's go. No, I looked into that, Philip, but that's really hard to basically build. And then I have space here for heatsinks if needed that I could case couple. But in the end, as you can see, it's likely not needed. Okay, let's start at 88%. I don't know why, but... Wow, it's drawing... Huh. Yeah, no, still pretty good. Likely it's just not achieving the waveform though, because as I said, there's those limiting resistors in there. So it's still drawing the power though. What is power maxed out? 139, okay. That should drop way more. Like that, okay. See what's happening to the power when I set it to 87% or when I set it to 77%? That's like half. So, oh, here we go. Here we go. We're at 100 degrees. Oh, you can't see it. MOSFET at 101 degrees. Let's see if we up the power. Oh, we're at 112, 115, 120, 125. We're cooking this MOSFET now. 130. Let's go a little bit higher. No, it's going down, it's going down. Probably because of the waveform, it just can't do it. Right? Because I have those limiting resistors in there. 79%. %? What was it again? 82%? Yeah, there we go. 82% is the sweet spot. It's going wild in regards to temperature. 130 degrees. I'm trying to have you see. 135. 137. Oh, we're smoking again. 138. Yeah, anyway. Yeah, so I could make that work if it needed to. But I explicitly designed it not to, basically. I always need to check LEDC output, because the more you up the frequency, the lower your bit depth will be. So with 19531, you have 4096 steps. But at 10 kilohertz almost, you have 8092 steps. That's also what makes analog dimming so much more smooth than our digital LED strips, because digital LED strips are driven at 8-bit, so only have 255 steps, while this, if we set it to, let's set it to this, that's also probably still high enough for the camera. We're going to have 8092 steps instead of 255 of digital LED strip. Yeah, Mr. Tech Gadget, maybe, but I could also make it work by designing it differently, but I considered 120 kilohertz max in my design, because if you want to run your LED lighting even higher than that, I don't know what you're doing. I don't think that's needed even for camera work and things like that. So, yeah. So now we're running at about 10 kilohertz, which is half of what we ran initially, because we were running around 20. And now this is nice and smooth. Oh. So even if we dim down now to almost nothing. So now you can see even at 10%, the LEDs are still lit. So let's go down even more, 5%. And you can see it's still smooth. Even at 5% now, the LEDs are still lit. Let's go to, I don't know, 3%. Okay, there were some harsher steps there, but now these LEDs almost aren't lit at all anymore, as you can see. 1%. Yeah, no, it doesn't do 1%. 2%? Can we do 2%? No, 2% is also too low. 3% barely works. But probably if we went down in hertz even more, we could do even lower percentages. Because there's just more steps available, and then if you change from one step to another, or in one set level to another set level, it'll just have more range to do steps, basically. And as I said, digital LED strips only have 255 steps per color, and this right now has 8,000. So that makes it way smoother. Okay, let's run this at, I don't know, whatever level. 90%. Well, it's probably still cooling down. The MOSFET is. Yeah, the slow-mo guys won't be able to use my boards. They should use constant current or LEDs at 100% output anyway, not dim down. And they need a lot of light, so they're not going to dim their lights. Anyway, this is going to be fine because this frequency is peanuts compared to what we just did. Yeah, so this is the version with Ethernet there, Jonathan Castro. The other two won't have Ethernet. So there's going to be 3 boards which each have different features. This has the very high power MOSFETs, easily do 10 amp per MOSFET if you want to do high power strip. But it also has the Ethernet jack, and it has a digital output like we tested in the previous live stream. And then we already looked at the AN Mini. That's going to be a nice 5-channel mini board. Slightly limited on power. Then again, 10 amps is still pretty good. This one will do 30 amps. And then we're going to have this guy. It doesn't have Ethernet because the ESP just doesn't have enough pins. But it will have external Wi-Fi like all the others. And this will be able to do 45 amps. And it'll have 15 output channels. And this is basically driven almost the same way as the AN Mini, except that this has the dual MOSFET gate drivers again, and the same MOSFETs as the AN Mini, except they're running at 10 volt instead of 5 volt. So where we could do 5 amps per MOSFET easily, all 15 of these will, well, easily do that too, because we're even driving them better. But let's say you need 15 channels at 3 amp output. Well, that's 45 amps. So that'll work great, right? But no Ethernet on this one either, because I said I don't have the pins. On the AN Mini, it's a cost consideration. So then there is the Hexa Hybrid, or whatever we're going to call it. And that one has the Ethernet, it has the digital output channel, and it has the 5 high-power analog channels. And yeah, so far it seems to be behaving great if I don't mess up the ESD chip on the USB port. Yeah, and this is now running around 10 kilohertz at 50%. Let's see if we can get the PWM on here. Let's see. This is 400 shutter, 2500 shutter. Okay, 10,000 shutter. Let's up that a little bit. I probably need to raise ISO. Hold on. No, what TV output in progress? There. Yeah, we're seeing PWM. I can see PWM. Because you now see the jagged lines there? That's the PWM. So let's see if we lower frequency a little bit. So at 3200. Don't know. Don't know if it's there. But then again, when shooting video, this is 1/1000th of a shutter, 1/1000th of a second. That's already fine. I mean, maybe slightly. But I generally shoot at 125. Yeah, that's fine. So let me lower the ISO again. Yeah, that's going to be perfectly fine. So yeah. Yeah. And I think that's going to do it for the live stream today. That was some good tests. And basically, if, you know, I'm tooting my own horn here, everything I designed for it to do what I wanted it to do, it seems to be able to do. So we had the AN Mini, and I kind of wanted the big output ports to do 5 amps and the smaller ones 3 amps. And the big outputs would have been fine at 4 amps too. But at 5 amps you can drive those high power strips for 5 meters, etc. And it'll do that just fine. And it has 2 positive outputs at 5 amps each. So that works great. And those non-gate driven, so directly from the ESP, also perform fine at 3 amps. So even at 5 amps they get 10 degrees hotter. So they're going to be perfectly fine at 3 amps. Right? And driving RGB CCT, which is probably what most people are going to do with this board, we're not going to get even close to those values, because the RGB CCT strip that was connected to it would do 2 amps or 2.5 amps on the white points, right? So 50 or no 40 watts or something. Easy. And then we have the I have another one here. The Hexa Hybrid, that will easily do 10 amps on its its big outputs, I guess I could call it. All of these are the same, except that 2 of the MOSFETs have 2 outputs to do power injection, and you can easily run 10 amps on those, 0 issues whatsoever. So that also meets the design goals. And since all of these are built the same, except these just have a little bit more space, I have no doubt there that you can run multiple RGB CCT strips, power injections, and I don't know what, and that's going to be perfectly fine. Cool. So that's good. That's what I wanted to verify for myself today, because, you know, I designed all this stuff virtually, and then I just, you know, hope it does what it should do, except that I always test if it'll do what it should do. And that's, you guys joined me doing that today. And hey, we got to melt together some LED strips today, because these are not going to come apart anymore, I think. Don't look at my face there. Yeah, these are probably permanently stuck together now. I don't know, we can try. Ow! It's hot. No, that's not coming apart. Oh, okay. No, I'm wrecking the roll. Wow, look at this guy. Is that my fingerprints? I don't know. It's hurting though. There's no secret time today, Philip and CJ. I don't have one. Do I have a secret? No, this is the secret stuff I'm already working on, so I don't have a secret. Sorry. Too bad. And also, oh, well, I guess we got to test that too. At reasonable PWM frequencies, these boards will also dim very, very low, which has also been a traditional problem with PWM boards. This isn't a secret anymore. I don't know. Okay, maybe a secret. I'm going on vacation next week. There, now you have a secret. Our LRS 612 did great. 0 PWM noise. The real secret was the friends we made along the way. Right? So, oh, that's actually a good one. We're currently at 10 kilohertz. Nope, I don't hear it. I'm going for a week to Egypt. We're going to go to a nice resort and, yeah, just lay there. I don't know. We'll see. That's true, Philip. But then it's a secret for all the other guys. So, you know. I'm probably going to be designing some fun boards there because I'm really wanting to do that, but I can't because there's also all kinds of other stuff going on. So I'll probably go swim a little bit and then design some boards because it's fun for me to do that. But, you know, we'll see. We'll see. Pyramid of Giza. We're not going to go to the pyramids, but that would be fun. Thanks, Chardo and Mister. Okay, we're going to just call it today, and thank you all for joining. I'm happy to see that these tests went great. These are perfect results in my book, versus what we had last week. But, yeah, thanks for joining, and I'll catch you guys later. Bye-bye.